And I think we need to move to our last talk of the workshop, which is by Brian.
Yeah, you can't get rid of me. I'm here all day talking all the time. So I will take over screen sharing from Matthew. And so Marco, I think you should be able to see my slides now. All right, cool. So hi everyone. This has been an awesome week. I hope you've had a lot of fun. I've had a lot of fun at least. And so today I'm just gonna close things out here talking a little bit about sustainability, which I think is a really important topic that we've sort of been going around and mentioning, I think, a lot this week in a lot of different ways. And so what I've been working on with a bunch of the folks you've seen this week and a bunch of the names you've heard, and I'll get all to that at the end. I got all their nice pictures on the last slide, is we've been thinking about what is the net impact of TinyML on sustainability. And so to us, the reason why we're thinking about the sort of like the net impact is that we know that TinyML can support some of the sustainable development goals. I mean, we've seen a lot of applications, and I'll highlight a couple at the beginning because it's always fun, about how TinyML can help with ecology and environmental efforts and food production and all these other sorts of things that are really, really, really important for the future well-being of the world. But the question is, TinyML is also going to have some sort of cost. And so we were sort of thinking about it here as saying, you know, there is some cost in energy and raw materials to manufacture a device. There is some cost in logistics to ship devices around the world. Then you can use it for TinyML. That's great. It's doing amazing things. But while you're doing that, there is some energy consumption cost. And then when you're done with it, maybe it can be upcycled, maybe it can be recycled, but some of it will become waste. And so if we start to try to account for all of these different things, what's the net benefit here? And this work that I'm going to present, I would say, is a first effort at trying to think about this in a holistic way. But you'll see one of my last slides is like, here are all the other things you should think about and we should explore, because it's a very, very complicated problem to try to collect and summarize the full net impact of all of this. So what I want to do today is walk through this in sort of 4 steps. So first, let's talk about some of the positive things. Let's start being really happy and excited. Then I want to talk about the environmental footprint of TinyML, and we're going to break it down first, thinking about a single microcontroller, and then moving to the full TinyML product or system that you might deploy. And then we'll think about what happens when you scale from one system into millions or billions of systems. So let's start with the positive side. I think actually this was covered a lot yesterday. If you think about the show and tell talks, a lot of these show and tell talks are about some of the amazing positive things that TinyML can do to improve the world and to help us with a lot of these, you know, important tasks towards sustainability, conservation, food production, animal tracking, all these sorts of things. So I just want to name that if you weren't here yesterday, you should check out the talks from yesterday. We'll try to get that all posted as soon as we can. And there's a lot of really interesting examples there, some of which are very similar to the examples that I had sort of put together, but I'll give you a couple. So if you look at Sustainable Development Goals 2 and 3, they're focused on zero hunger and good health and well-being for all. And so a couple of really interesting, exciting examples that we wanted to highlight were, one, there's this plant village project, and they have this app called Nuru. And what they've done there is they've deployed this in Africa into the fields to say, hey, you can take a picture of the plant and it will tell you whether or not it's healthy. And the beauty of having this sort of edge ML device application is that it's not actually going all the way to the cloud all the time, right? They've loaded a lot of the information onto the device. You can do it with low connectivity, and it's pretty lightweight. And so these devices, especially with their radios turned off, can have pretty good battery life. And it was reported that like one farmer had 55% higher sales and 146% higher yields in her fields. And so that was sort of a really, really impressive number to me. And I thought this was a really wonderful example of where you can go to fight global hunger. Another thing that was really interesting is that there was a report that said if you do targeted spraying of pesticides, so if you go around and you look at where you should spray pesticides, instead of just blanket spraying a field, you can actually use 0.1% of the pesticides that you might need if you were doing sort of blanket spraying and still get the same sort of impact of removing pests. So that was pretty inspiring to me. And I look back at, Bart's talk from earlier today, and I'm like, hey, tiny drones, swarm a field, spray these targeted pesticides, and really reduce the use of these chemicals, which can be harmful when used in large amounts. Another interesting one is against mosquitoes. So there's been some prototypes that have found like 80+% accuracy of recognizing mosquito wing beats. And so there was one project that I saw that was really cool where they put this little device in like a pond. And when it heard the mosquito wing beats and sort of realized that it was laying its eggs, it basically had a little agitator that would just sort of spin and cause the water to kind of shake. And it turns out that mosquito eggs, if you do that, it can actually remove the ability for the eggs to correctly process and for the mosquitoes to actually correctly be born in that stagnant water, right? So the mosquitoes need stagnant water. You can agitate it, it becomes moving water, and now you've broken the mosquito life cycle. And so that was a really interesting idea because they had this little device sitting in the pond, and to save battery, it had a little solar panel on top. And to save battery, it would sort of sit there and wait. And when it heard the wing beats, just like you might say, okay, Google, or hey Siri or whatever. Oh, I'm sorry. I apologize if I turned on your smart devices. As much as you would say that, it sort of did the same thing. It heard the wing beats, agitated the water. So these were, there are tons. I've got 2 more slides of fun things because I like these fun things, but there are tons of different things. Here's just some examples of how we can work towards that. If you think on life on land and below water, Rainforest Connection, really cool company. They're using recycled smartphones, a little bit, say, higher compute than a TinyML system, but showing the promise of being able to take some reduced compute device, build some sort of solar power station. They're listening for deforestation efforts. And so when they hear that there's, chainsaws going where they shouldn't be, sends out a ping, right? And again, this whole sort of concept of deploying this edge device, saving the battery, and then sending out the ping sort of when you need it, really, really powerful, right? If they can process on device, then they can just send out the pings when they need to. There's a bunch of different efforts towards elephant tracking and identification. One is Resolve AI. They can run for more than 1.5 years on a single battery to try to detect elephants. There's also been a bunch of animal collars, smart collars on the elephants that listen for gunshots to try to find poachers, and then they'll ping out when they hear it. And those last a really long time. And so there's just like a lot of really exciting and interesting examples of doing that. And in fact, actually, a couple of folks have used TinyML on elephant collars, and actually to build smaller collars that you could put on say, maybe even a lion, because a lot of those devices weren't having good battery life. But when you bring in TinyML, instead of trying to consistently stream, real-time audio, you can instead listen on device, turn on the LoRa, send a small ping when you need to. And finally, this is actually being used underwater too. So Google deployed some hydrophones in Vancouver Bay, so there wasn't any more whale strikes. Pretty kind of cool as well. Okay, last slide of positive things, but they're fun. So climate change. Ribbit Network has these little devices. It's crowdsourcing the world's largest greenhouse gas emissions data set, which is pretty cool. And Matt actually knows a lot about this kind of stuff. And he was saying that this actually allows you to have slightly more accurate information than even if you were taking what we're currently doing, which is large scale satellites looking down on the Earth. You can get good information at a high level, but you can't get that localized information. And so these distributed sensor networks can actually do it. So that's really exciting. Back to the robotics. The bees are dying. It's a problem. Colony collapse disorder is a real issue. And so there's a project going on at Harvard to try to design these little robo bees. They're tiny. Like, you think that the drones that Bart showed you were small. Like, these ones are the size of a coin, and a small coin, to be clear. A US penny is like, this big. So it's very, very, very small. And so we for sure need the tiniest of TinyML if we want to put intelligence on these sorts of devices. And finally, and this one will come back later, there's actually a bunch of reports that just doing a smart HVAC system can do a 20 to 40% reduction in building energy usage, right? If you don't run the AC, if you don't run the heat when you don't need to, when people aren't in the room, if you can modulate the temperatures during certain times of day, you can save a ton of energy. And so these devices like the Nest thermostat shown here are phenomenal, but like still a couple $100 US. And so you can imagine with some sort of TinyML systems, we could bring these prices a lot down and start to have some of that energy reduction more globally and more sort of at scale. So that was just sort of a tour of some possible fun, exciting, interesting applications. But there are tons more. We saw more yesterday. TinyML can be awesome. But, and this is the big but, this is the big thing that we wanted to really look at this study is, not only can it be good, but it's a physical piece of hardware. We need to make it, we need to produce it. What's the impact? So we started with an individual microcontroller. A lot of this is based on this report from ST. You can see the link sort of at the bottom, and I'll post all these slides so you can get this. And they were looking at impacts to climate change from CO2, how much water was used, freshwater eutrophication. So it's putting certain chemicals in the water, which is causing these algae blooms and protochemical oxidant formation. So this is the release of certain chemicals that really hurt the ozone layer. And what they were looking at is, hey, if we break down the lifetime of a microcontroller into production, and if we break production down into energy usage during production, and then everything else during production, if we look at raw material extraction, if we look at the use of the device, so that's mostly electrical power consumption. If we think about logistics to ship the raw materials, to ship the device, to move that all around the world, and then if we think about end of life, what is the trash cost of these sorts of devices, we can start to build some plots and start to understand not only what is their impact, but where is that impact coming from and how is it impacting some of these important environmental concerns. And so here's a chart I'll build up for you, but the high level summary is like, it is production, right? So for microcontrollers, across all these different environmental indicators, like more than 50% or almost 50% in all cases of the cost is from production. And of that production cost, most of it is energy consumption. So this is both, this raises two interesting points, which is one, and I think the pop-up slide is in the wrong area of my build here, the little summary, but if we can reuse and recycle these devices, we've eliminated a large portion of the cost, first of all. And then second of all, if we can use more green energy to get that energy, right, then that will also greatly reduce the cost here. And so this really bodes well, in my opinion, for TinyML, because most microcontrollers, or many microcontrollers out there today, are good enough to run TinyML. So we can use them for a while. And with all the efforts towards green energy, that will further reduce any environmental impact of these devices. But if we build up the rest of the chart just for finishing it off, raw materials is another huge portion of this, extraction of these raw materials. And again, reuse, recycling will remove the need for that. And then the use one, which is basically the rest of it, is again mostly energy consumption. So again, basically, if we can reuse them, and in using them and in making them, if we can use more greener energy, we can eliminate a lot of the cost here. Yeah, so that was that takeaway there, which is pretty exciting, and surprisingly to me, right, was just that how much of this was production, right? The use of a microcontroller is not that bad. It doesn't use a lot of electricity, it's pretty low power, and most of the cost environmentally is from producing it. Now, the one thing I want to also note though is, like, if you look at the title of the slide, right, it's energy consumption during production dominates the small footprint. And so you're like, okay, but like, what does small mean? So provide you with a couple of different interesting points for some context. So the total impact here, if you think about a climate change indicator, might be a CO2 equivalent produced. And so the whole lifespan of a microcontroller is around 390 grams of CO2 equivalent produced. That's the same as driving like 1.5 kilometers in a car. Very, very, very little. I would argue probably that the average amount of car driving today by everyone on this Zoom would get us thousands of microcontrollers that we could use, or maybe because it's a Zoom and this is remote, you didn't go anywhere. So wonderful. We've done well. Use TinyML, don't go to work remote, and you'll be okay. In terms of water demand, it's 23 liters. That's actually not nothing, but it's 23 bottles of water over the lifespan of the microcontroller. Now, if you notice, actually, a lot of that water is in raw material extraction. So if we can find better ways to extract some of these raw materials, we might be able to reduce the water cost there. And again, if we're reusing things, that sort of entire block goes away. Freshwater eutrophication, it's 120 milligrams of phosphorus equivalent, phosphorus being one of the main things that can cause a lot of these sort of algae blooms and issues in the water. It's 0.2 of a washing machine cycle. So you get 5 microcontrollers, run your wash once. I know many people run their wash every day, so you would get thousands of microcontrollers a year for that. So again, not a huge impact there. And finally, for the protochemical oxidant formation, again, it's a very small amount of driving. It's less than 3 kilometers. So microcontrollers actually not that bad for the environment to produce one. Not nothing, but not that bad. And a lot of that cost is in production, not in use. So this was sort of inspiring and made us think optimistically about what the total cost would be. And so then we wanted to say, okay, so we know a microcontroller is pretty good. Let's look at a full TinyML system. And so, that sort of begs the question, like, what else is in a TinyML system beyond our little microcontroller? This, by the way, being an image of the particular microcontroller you'll find in the Nano BLE 33. This might not be the exact packaging, but this is that microcontroller. So what else is in there? Sensors, casing, power supply, all the little, everything that makes it the physical board, right? It's not just a chip. There's all these peripherals that you need to get to a full TinyML system. And so, for example, if you look at the Nano 33 BLE, this chip is sort of sitting somewhere inside this gray box. And in fact, that gray box is not only the microcontroller, it's also the BLE module, which is a whole nother thing. And so really, it's not even the whole gray box. It's like a small little part inside of that gray box that is just the chip itself, excluding a lot of the BLE stuff. And if you look at the physical board, you can see there's a lot of other stuff there, right? There's all the other little sensors, there's the buttons, there's the USB connection, there's all the pin header holes and all this other sort of stuff. And so like that's a full TinyML system. Actually, in fact, that's not a full TinyML system. It does not have a battery. It doesn't have a power supply. But that's sort of an example of showing you just sort of like pictorially how little of the system the microcontroller might be. Hint, hint, it's not going to have a lot of the impact. So we built some representative systems. We thought about sort of like a high cost, medium cost, low cost system to try to understand what's going on here. And so we went across 2 different applications, image classification and keyword spotting, sort of being very popular TinyML applications, felt like some very representative ones. And the reason we were using different applications is because there's going to be a different size to the device, and there's going to be a different kind of sensor in there. And it turns out a camera is a lot bigger than a small little microphone. And so if you want to think about sort of this high, medium, low cost, you can think about the TinyML kit is kind of chunky, right? Like we have a pretty big board. There's a separate discrete camera. There's a separate discrete microcontroller. You plug it all in together. It's wonderful for prototyping, but I wouldn't call it like compact. So that was sort of an example of what a high cost system might be. The useful sensors, version 1.0 person sensor, to answer somebody's question before, like maybe you can buy it, you should ask them. They did make one. It does exist. They might be selling them. I don't know if they're selling them one-off. They might be just selling to commercial clients at this point, but they have this sensor and it's tiny, right? And it's all integrated, right? So the microcontroller and the camera and everything are put together and compact on one little board as small as they can. And then if you think about the low-cost keyword spotting, I sort of like cut off part of the Arduino, but like the microphone is just that little tiny black thing here. And so the microphone is a very, very, very small sensor. And I sort of want this for scale, you know, the microphone is smaller than the microcontroller, the camera is probably bigger than the microcontroller, right? And so that's why that's medium versus sort of low cost. So what happens if we do this? First of all, this part in blue that I've sort of highlighted across here, that is the microcontroller life cycle cost in kilograms of CO2 equivalent. So for the rest of this, we're going to look at just the climate change indicator, just to keep things a little bit simpler. So the microcontroller is a tiny, 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 tiny portion of this whole thing. In fact, the majority of it is all the other stuff, the power supply, which is the battery, the sensing module, which might be the camera, the casing, which is just all the, you know, the physical like plastic that it's sitting on, and all the other stuff, you know, fills most of the rest of the bar actually. There's a tiny little bit for ML model training. We did consider, you know, not just power usage of the MCU, but also power consumption to train the model. Still turns out, right, TinyML models are very small. They're relatively easy to train. So still that is a very, very small sliver. And then there's a bit more on sort of the gray here being transportation, as in like physically shipping the devices. Can be really small in the low cost scenario, gets a little bigger in the high cost scenario, just because the thing is bigger, there's less boxes that you can fit in sort of in a truck. This was sort of thinking about the full system, about what it could be. Your question then might be, okay, that's nice. Like, what does this mean in context? So if you compare this to, say, an Apple Watch or a MacBook Pro, will be 5 to 38 times less better, I would say, in terms of, you know, impact. And by the way, this is a log scale, so you know, it's orders of magnitude every big line, and will be, you know, 50 to 380 times better than sort of a MacBook. And this is based on sort of a 3-year lifespan for the device, because that's what Apple uses for their devices. So TinyML systems, even in sort of our like kind of worst case estimate, pretty good, and our best case estimate really good. And we can find ways to work this, because if you sort of are thinking about the chart, like a lot of this cost is just transportation and casing and sort of overall design. And so if we can make this run with less big of a battery or a small solar panel, or we can work on sort of the casing to make it more compact and find, you know, the right sensors to use in the right cases, or use lower cost sensors or smaller sensors, we can really bring down that cost already more, and it's already like actually pretty low cost. So again, we're feeling like, all right, TinyML might be good, might be okay. We have all these positive things, and the environmental impact of the individual devices is probably pretty small. Oh, right. But before I think about scaling it, I just want to note that we actually, and I give all the credit to my co-authors. I did not do this. This was Mark and Shvetang who made this, but there's a website we put together with a little calculator that you can go to. So if you don't like our large, medium, or small, or you are designing some sort of custom device and you want to think about what the environmental impact might be, if you go to this website, and there's a little QR code here that'll take you there, or it's just it's harvardedge.github.io/tinymlfootprint. We built an online tool, an online calculator. You can kind of go through and click, you know, what kind of sensor do you want? How much training do you think it's going to take? And there's a bunch of these lines here that say like custom whatever. You can type in any number you want. So if you don't like some of our presets in terms of, you know, what we think are some example settings for a TinyML system, you can go in and say, actually, I'm going to put in a big number here. What happens? And it will compare your device to the MacBook and the Apple Watch, and it will also break down your device into its components, as we sort of had on the previous slide. So that's a fun little tool we put out. Yeah. So you use the tool, you found your device or all the devices. We have these high, medium, low cost scenarios. That's great. We've done one device. It's not that bad. But the question is, there's a market forecast that says there's going to be a lot more TinyML. There's going to be a lot more devices. So what happens when we scale these numbers to millions and millions of devices? And the real question is actually, it's two-part. It's one, what happens when we scale it, but also how many devices should we scale it to begin with? So the first thing we did is we were thinking about how many TinyML devices are there and how might we just come up with some estimates. So there are around 250 billion microcontrollers deployed today and around 15 billion IoT devices. And since IoT devices are a really good proxy for TinyML devices, yes, not all of them can do TinyML. But you can imagine that those are the sort of devices that will be the first ones to become TinyML devices. So we said, okay, let's assume there's 15 billion TinyML devices today. Let's assume some sort of linear growth and exponential growth based on some data from Statista. You can look at the actual data on the IoT devices there. They project linear growth. So we also said, let's model exponential. That gets us to around 100 billion devices in 2035 or 2036 or 2067. So not for a little while. We'd hit that 250 billion mark of all the microcontrollers deployed today, not until 2144 if we take Statista's linear growth model. If we do an exponential model, we'll get there a lot sooner. We'll get there in 2043, but that's still in more than 20 years. And then we've included the trillion number just for funsies. Exponential growth is terrifying. You can look at how much longer it takes, right? The linear model doesn't get there till past 2500, whereas the exponential model gets there by 2053. So exponential growth can really sort of take over. But in either case, we're looking at a very, very conservative estimate of saying we have 20 or more years until we hit 250 billion microcontrollers, and probably a lot longer. So we said, okay, let's just take that 250 billion number and assume that there's 250 TinyML devices right now. What is the environmental impact of all of those? And we also said, if we're going to make these conservative assumptions, let's assume that high cost case we used before. So worst case assumption, 250 billion TinyML devices, all at that super high cost size. That would give us 1,765 million metric tons of CO2 equivalent. Oh, no, of metric tons, because it's tons. That's 1765 metric tons of CO2 equivalent, which is nothing to snooze at. That's actually a lot of emissions. But if we say go back to the positive, there was that 20 to 40% improvement in building emissions that you can do from smart devices. Let's assume we're all on the low end. So again, let's take a conservative assumption and say we're only going to hit that 20% improvement. And let's say we can do that with these 250 billion TinyML devices. We can hit that 20% improvement for the building sector in general. And actually, we're not even going to do the whole building sector. We're just going to think about residential homes. So we're, again, being super conservative and going off of some data from the EPA. That would already save 1,181 metric tons of that footprint. And if we go across the rest of the data in the EPA and we assume a 0.6% savings in every other sector over 3 years, we'd break even. And so this to us was like pretty inspiring, because it was sort of saying, if we take this like one small sliver, like residential homes, put in some TinyML devices, we can already recoup most of our costs in 3 years, and then barely do anything good everywhere else. We're back to break even. And if we say hit 20% savings across everything else, that gives us another 18,000, 19,000 improvement, and we're way positive, right? This is the total emissions. We're at super negative emissions here, and that 20% number is probably definitely too much. But also, this is only assuming a 3-year lifespan, and so if our devices have longer lifespans, this data starts to look even better, right? If we say that these devices are going to just sit there and help this home for 5 years, 10 years, suddenly we're already net positive just in the residential sector. And then you do anything on all these other sectors and we're getting huge improvements. So this to us is our sort of cautiously optimistic conclusion that says, there will be a cost to TinyML devices. A lot of it will be in production of new devices, mainly in the energy consumption just used to produce these devices. But if we can reuse them, if we can keep them in the field for a long time, and we can even have some of them working towards all of these many, many, many positive things that TinyML can be used for towards the environment, TinyML should be a positive impact on the world. That said, lots of limitations and areas for future study, right? We just looked at carbon here on the net impact. But if you remember back to the slide where I was talking about the cost of an individual device, there are lots of other potential impacts. And so we actually need to do more work to look at the break even there. I'm hopeful that given how the break even played out in carbon, that it is likely that we'll see similar things where these devices are small, they don't have a huge impact, especially if we're using them for long lifespans. They should be positive, but there's no guarantees, and we should do more study there. Another thing to keep in mind is Jevons paradox. This is the idea that when you make something more energy efficient, sometimes you just use more of it. This comes, I think, from the coal industry, where once coal engines became more efficient, people started using more coal because it was cheaper to use these sort of engines. In this case, we think our 250 billion TinyML devices deployed instantly right now is a very, very conservative estimate. And so we're hoping that we capture a lot of Jevons paradox in that, and we can still come up with this positive conclusion. But the one really important thing that we didn't consider here is we're just looking really at the net break even and the metrics around environmental impact. We're not looking at the human costs, right? So one of the big things that came up was, so water usage was pretty high in terms of just raw material extraction. Well, raw material extraction has a huge human cost and a lot of people all over the world. And so if we're using millions and millions more devices and requiring a lot more of some of these rare earth minerals that are pretty nasty to get, there's also a huge human cost here that we need to factor in. Again, I'm really hopeful that we can just do more reuse of existing microcontrollers instead of requiring many, many more new ones, and that will get around a lot of these problems, but it is something important to consider. And then finally, on like sort of the positive side for future study, how can emerging technologies help? There's a lot of them, and there's a lot of really cool ones. One in particular, there's these like flexible things that you can use, and you can get, instead of using like a silicon hardboard, you can build on these flexible surfaces. And there's a couple companies working on this, and some early reports from some of these companies are noting that it's like 2-3 orders of magnitude more environmentally friendly to make them and to throw them out. And so since most of our impact on TinyML was just on production, hey, new technology that removes that as being a problem, that would be kind of amazing. And then again, I'll hammer it home, reduce, reuse, recycle. This sort of recycling point, I think, is a really big one to think about with regard to TinyML. So that was sort of a brief tour of some work that we've been doing recently to try to think about the environmental impact of machine learning on microcontrollers and just this overall sustainability of TinyML. This is a link to our white paper that's out. We're actually actively working on a revision that's even better. So if you check back in a couple of months, there should be a new version up there that is better writing, but all the data stays the same. Just some additional analyses that you saw today are not in that older version of the work. And this is very highly collaborative work with, so Pete is over here. He's the guy behind Useful Sensors. He's at Stanford. That's Vijay, who you've heard a lot about. You see Colby and Matt on here, who've talked to you this week. Shvatank is the first author who's leading a lot of this work, and Mark, who's also at Harvard, has been a big part of this effort as well behind the scenes. So that is sort of all I have on this in terms of me talking at you. I would love to hear any sort of comments and questions. I'll open up the chat and start trying to look through that as well.
Super, excellent talk, Brian. Thank you so much. That was an fantastic kind of closing talk for the workshop. I think it covered many of the issues that were discussed this week. Okay.
So I'm
are
looking
you?
through,
Yeah.
I'm looking through the questions here. Somebody's asking about how can individuals contribute to this? What does it mean to reach end of life? Yeah, it's sort of mechanical breakdown of components. It could also just be that the particular device is so old that it's not really useful anymore. You can imagine there are sort of computers that ran on like a 4-bit architecture, and now everything today is on 32-bit architecture. And so you just like actually can't get the software to run on there. My hope is that since a lot of microcontrollers support 8 and 16-bit integer compute, and a lot of them actually do 32-bit and have floating point units, we can quantize models down to 8 bits or 16 bits relatively easily for TinyML. And if it's 32-bit float, oh my God, like we can just run standard TensorFlow models. So since a lot of microcontrollers actually can support this kind of software, my hope is that that end of life thing, we're making like very, very, very conservative assumptions, so we can just reuse these devices for a while. I mean, I think especially in TinyML, where we want just a simple model to do a simple task, we can get away with using some of these older and less capable devices. How can someone get the TinyML kits? Okay, so the Arduino kit that we've been mentioning a bunch is available on Arduino. If you just like Google Arduino Tiny Machine Learning Kit, and maybe somebody can drop a link in the chat, you can find it. They're about 50 or 60 bucks US. And that's sort of the kit. It's a good way to prototype, but there are a lot of other devices out there. If you look at some of like Marcelo's projects on like his Hackster.io, there's some ESP32s, there's the Zhao devices from Seed, there's just a bunch of other devices out there. Some of them might be more cost effective in your area of the world. It sort of depends on where things are shipping to and from. And there is more or less documentation on a couple of them. We sort of had settled on the Arduino one originally just because there's a lot of good documentation on Arduino, so we thought it would be an easy platform for folks to use. But there's been a growing amount of documentation on some of these other ones, and so you might be able to get away with lots of different kinds of devices. For people who need to leave early for Ramadan, of course, have a wonderful evening. Eid Mubarak. I hope you had a nice fast. Oh, somebody already provided the link. I should scroll down farther. Could a sensor be extracted from any end-of-life device and transformed into an ML sensor? Ooh, that's interesting. Probably. Most of these TinyML devices are essentially just using old cell phone cameras. So I imagine if you're very good at very fine soldering and wire connections, you could definitely extract cameras from old cell phones. In fact, you could just use an old cell phone. The processor on there could definitely be repurposed in some of these sorts of devices. It might just require a little bit more manual work for you to get the necessary firmware sort of installed on the device. But there's no reason that any of these old cell phones, which a lot of them are using ARM, Cortex, et cetera, couldn't be reflashed with some of this new software. What are some of the practices your lab does to ensure sustainable development? Good question. Best practice. So in the reuse sense, I like to reuse a lot of old computers. I have a lot of old desktop computers that I've repurposed as sort of lab machines, and I've flashed an old Windows computer with Ubuntu and using some old CPUs and GPUs to run some test stuff. I think I haven't done a lot of work with large models, but I think that's a really open question around when you're using some of these large LLMs, how do you account for the environmental impact of some of those sorts of use cases? I mean, I think for me, a lot of my research has been on how to get things on the edge. Like, how do we actually get some of these advanced algorithms running on, if they were running on a server, how do we put them on a laptop? If they're running on a laptop, how do we put them on an embedded device? And so my hope is that by trying to think about that, we are spending a lot of time taking a step back and trying to design software that can run with less electrical usage, or extract information that can run on things that will be better. And so our testing shouldn't be too bad because I'm just running a laptop computer for a day. Once we develop that, we can release that to the world and hopefully move things onto those sorts of sorts of systems. I think the other thing for me personally is that I think a lot about open access educational materials. So all this TinyML stuff and whatnot. And I hope that by releasing that, that helps with scalability. And there are more folks thinking about this problem so we can improve that, you know. And then I try to keep talking to Marco because he knows all the folks at the UN and the ITU and whatever. And I just say, how can I help? And so hopefully we'll do some more stuff there. A bunch more links, link to the Zhao, a bunch more thank yous, links. For beginner TinyML, what steps would you recommend to become more familiar with hardware and firmware side of things? Yeah. Okay, so one thing you can do is the edX TinyML course was built like a year before things like Edge Impulse existed, or as they were coming out. And so we used a lot more, TensorFlow 1, Google Colab provided a lot more lower level code. And so that might be a good place actually to start because there are more examples that are a little bit lower level in terms of like the C++. If you want to go really deep into the hardware firmware side of things, maybe follow up with a note to me later and I'll have to ask because I haven't gone as much that deep. But I know a lot of folks who have, so I might be able to, put you in touch with some folks or try to think about some of that. But I do think like if you're a beginner and you're not as happy with C++ coding, I would start through the Edge Impulse path. And if you really want to see some of that other lower level stuff, maybe take the edX course. If you really want to get good at it, a lot of the edX course examples are in TF1 because we produced this when TF1 was still a thing. Now it's TF2. I've sort of like added some stuff to the top of some of the collabs, like uninstall TensorFlow, back propagate all the software, like revert to old things. And I think a lot of the scripts are still running. If you want to try to upgrade those to TensorFlow 2, that would be a hard exercise in dependencies and working on some of this code. So that might be a nice challenge. And I would be forever in your debt for upgrading all of our things. So that might be a fun, selfish plug for a challenge somebody could do. Marco, I think I've gone through most of them in the chat. What I don't know is if anybody else has their hands up or if you or anybody else has any other questions.
So the plan now is to have like few more slides, like with some links and like kind of closing, considerations, and then we're going to have breakout rooms. So I would suggest if you have like kind of beginner's question, we're going to have a beginner breakout room. So we still have 45 minutes. So let me, and thank you, Brian. Again, it was an excellent presentation.